anything for a while. Uh-oh. You all right? Okay. All right, guys, so we're about to get into chapter 4, which is all about probability. Like the probability of charge to beat the Seahawks, for example, was low enough that made me happy that it happened. Go right at Sherman. Go right at him. Show me what you got. Nothing. That's what I thought. Oh, sorry. Sorry. So, we talked a little bit, very tiny bit about probability. We've done a couple of things about probability. We did the birthday thing the first day. You guys remember that? Seems like forever ago. I can't believe how many freaking weeks. I don't know what week this is, but it's more than it feels like. Good Lord. So I remember a long time ago we did the birthday thing, and I ended up having 4 or 5 pairs of people with the same birthday. That was kind of cool, right? We talked a little bit about the Monty Hall problem. With the way they used to do the show before Mr. Brady took over. These 3 doors. And it just freaks people out that if you pick one and then the guy opens one of these other 2, it's actually better. It's twice as high of a chance to win if you switch doors. So there's a lot of probability. Our brains are not hardwired to understand probability, nowhere near. So we have to kind of force our brains to think about probability because we're used to dealing with averages. We're always dealing with averages. It's always the law of averages. That's why if something happens as a low probability, we're freaked out about it because we always expect things to happen that, of course, now I can talk about it like this. We expect things to happen in here. Not here, and that makes sense. But what we get is people believe that this will never happen, which is unfortunate. So, for example, the 3 Mile Island accident. This is a long time ago, but you guys have heard of this? You know what 3 Mile Island is? The island that's 3 miles. No, if you watched, which X-Men was it? Wasn't it X-Men, right? Where they had the dude, Wolverine and stuff. No, all right. You guys and I don't watch the same movies. But they actually went to 3 Mile Island, and that's where they had Ryan Reynolds, and they morphed him and all this kind of crap. Let's get back to statistics. So, 3 Mile Island is kind of cool. There's something called normal accident theory. So what's it called? Normal accident theory, where you need a certain number of things to go wrong. So, for example, this gauge isn't working, and the backup gauge, somebody put a Post-it note over it. And this guy is supposed to check it, but he was out sick and somebody forgot to come in for him. All these things have to happen in order for there to be this and looking back, they said, holy crap, a lot of these things, everything that had to happen kind of happened for this, and that is going to happen. Statistics says it is a low probability, but it's not 0. So it will happen given enough time and enough of these situations, something will happen. You guys kind of with me? So it kind of flies in the face of what we expect, yeah.
And do we kind of have to measure all the variables for it to not happen?
So it's impossible.
Yes.
It's a human endeavor to make there never be mistakes. But it is so desperately impossible. You just can't.
Yeah, I know.
That doesn't mean you just sit back and you accept it. You can make the probability really crazy low that a major something's going to happen, but you can't make it 0. There's always a chance that this light's going to burn out that normally would flash red, or that I'm going to be standing in front of the screen right when it starts flashing something. Or, there's a chance that all those things will happen at the same time, and then something bad happens. You kind of with me? You can never control for all of it. Now, I'm not trying to, let's all go under our beds and just hide there. That won't help because, duck and cover just doesn't work. But that's something to keep in mind. That's a good example of how probability is nowhere near what we expect it to be. So if we go in and there's a 99% chance that the surgery's going to be fine, I could be part of that 1%. It's possible, right? Or if there's a 90% chance it's going to rain, and then it doesn't rain, and everybody's like, you said there's a... Well, dude, that was a 10% that just happened, dude. What do you want from me? right? So we have a completely wrong perception of what probability is and what it means. This guy was, what was the idea with this guy? If I choose door number 1. I didn't expect that reaction. So unexpected things happen. Now, of course, Monty, now what's behind 2 of these doors? Goats. And behind one of them is like a boat or a car or something, or a we will pay off your student loans, right? That would be nice. Well, it's too late for me, but maybe, or I pay them all. Now, he's going to open a door. More than like, what's the chances that you picked a goat?
33.
What's the chances that you picked a goat?
50.
Oh, 66.
Yeah, be less specific. 2/3. 2 out of 3 chance you picked a goat, right? Because there's 2 goats and 3 doors. So what's the probability? Now this is the most basic idea of probability. It's called empirical probability. Actually, this is theoretical. Because do I have any goats up here? Not that you know of. We're not picking any doors or anything. So this is really just the fact that there's 3 possibilities and 2 of them match what I just said. The probability of a goat, that I pick a goat, is 2 out of 3 because there's 2 goats out of 3 choices. Just like the probability I'm going to roll a die and it comes up a 2. It's probably that. 1 out of 6 is one side adds a 2 out of 6. And I'm not talking Dungeons and Dragons crap. Don't bring that into play. Well, if it's 20-sided die, you could not. That's good. So there's a 2/3 chance I picked a goat. So even just based off of that, now somebody could give me more information. If you could eliminate one of the doors, of course I would switch. There's a 2/3 chance I'm screwed at the offset. So if this guy opens this door and there's a goat standing there, and this is my goat. Oh my God, poor little thing. Let's do this. There's a goat there. Yeah, he's had some rough times. That cloning didn't really go well. It said sheep would strike goat. No. If he opens this door, it's a goat, there's a much higher chance that this is the prize. Why did he open that door? There's 2 reasons. He could have opened up either one because you picked a prize. But what's more likely, he chose that one because this one has the prize. Right? Say again?
I'm sorry, I don't understand.
That's right. So there's a 2/3 chance that the door you picked has a goat behind it.
Okay.
You with me? So he opens that door. Now, why would he open that door? Because the other door probably has the prize behind it. Now, maybe you picked the prize, and he could have opened either of these doors. Now, why wouldn't he open the door with the prize behind it? Because then what would be the point of him saying, you want to switch? Yeah, I got my eye on a certain goat, and I think it's behind it. No, I mean, that's a little weird, right? You guys semi with me. This is definitely going against our intuition. Our intuition would say it's 50-50. You cut a door out of there and it's 50-50. But we're forgetting that Monty Hall had information about stuff that we don't know. So the fact that he chose that door improves our chances if we move over here. 1/3 of the time, if 2/3 of the time I picked a goat, and that's a goat, right? 2/3 of the time this is a goat. How often will it be that I picked a prize? 1/3. So this must be the other 2/3 of a chance that the prize is here, because he eliminated that door for me. So I improved my chances by double. Now, does that mean if I switch, I'm going to win every damn time? No, and that's where people don't understand probabilities. They think it's 80%, so it's definitely going to happen. You just contradicted yourself. It doesn't make any sense. There's still a 20% chance it's not going to happen, right? Okay, how are we doing so far? Okay, so this is definitely, I want to just kind of go back to this a little bit because we talked about this one earlier. But it's definitely, it freaks the hell out of people, this problem. But it's because somebody was involved that had information that we didn't have. They knew what was behind the door. That's why they picked it. That's why our chances improves if I choose this one, because he probably didn't pick that one because it probably had the prize behind it. Okay, so let's take a step back. The important thing right now is how you guys got 2/3. That's the most basic definition of probability, is how to set them up. If I have 52 cards, and 26 of them are red, 26 of them are black, 13 of them hearts and diamonds, right? 13 spades, clubs. You guys with me? So even if you don't know cards, how many of you guys really don't know cards at all? Most of us, okay. Some of us don't know at all. Okay. But this is the basic setup of cards, right? There's red and black. There's hearts, diamonds, spades, clubs. Each one of these has 13 cards. Ace up to king. So ace is, let's consider ace 1 right now. Up to 10, 11, 12, 13. So jack, queen, king. How you guys doing? So how many kings total in a deck of cards? 4. 1 for each suit, right? So what's the probability if I had a deck of cards, if I picked, what's the probability I would pick a king? Yeah, exactly. So why would somebody say 1 out of 4? What's their incorrect thinking? They're stressing, they're thinking themselves there's 4 kings, and I'm going to pick one of those. Well, you're being way too optimistic. There are 52 things you could pick, and out of those, there's 4 things that you want right then. If I want to get a king, so probably I'm going to pick a king, 4 out of 52, and that reduces to something interesting. Go even one more step beyond that.
113.
1 out of 13, I like that. And of course, how does that relate? Every 13 cards, there's... Now, does that mean that if I shuffle a deck and I do 1, 2, 3, and I count to 13, the 13th one is a king? Yay. No, that means on average, there's a king for every 13 cards. You with me? So there's some acceptable number of cards, more or less, that I could do before I hit a king. Right? There's some standard deviation involved there. We're going to learn about how to deal with percentages and how they turn into means and standard deviations in chapter 5. Okay, so go on with this thing here. Let's probably pick the king of hearts. Yeah, 1 out of 52. Why did it go down, of course? There's only 1 king of hearts. It's got to be king, and it's got to be a hearts card, right? So it seems like and cuts things down, because and makes more and more requirements. So I don't know if I've told you guys about the big book. Nowadays we have it online, but there used to be a giant book in the financial aid office of scholarships. So you go to the financial aid office. This is, back when I was in college, which was, the internet was just rolling out. Al Gore was finishing it up. And you go there and you pick up the giant book of financial aid. You'd open it up and you start down this list. You must be under 30. Check at that time. You must be a math major. Oh yeah. You must be this. You must be that. You must be this. You must be a woman. Shit. Okay. Next one. I'm serious. They would have these. They should list those at the top. Don't put you must be half a Native American at the bottom. Put that the first thing, so I don't waste time. So and you must be this and this and this reduces probabilities, reduces the chances you are matching. You with me? What have I said? Probability of king or jack?
8 out of 52.
Yeah, where the hell's 8 coming from?
There's
Yeah.
4.
How many match what I'm looking for? 8 total cards matches what I'm looking for. I have 8 chances to match what I need for this statement. I have 4 kings and 4 jacks, so I get 8 things out of 52. And that reduces to 2 out of 13, which makes sense. 2 cards per suit. That would give me what I need. How are we doing so far? So or, what does or seem to do? Or makes it more and more likely, because you could be this or this. If it would have said or a woman, I would have been still good, right? I would have been excluded. My probability wouldn't have gone down. It would have went up. More and more people, a higher percentage would match. So what about if I say king or club?
13 and 52.
8 out of 52.
How many clubs?
13.
13, right?
Oh.
How many kings? So what's wrong if you say 17 out of 52? Why is that wrong?
Because king is club.
Because you counted one twice. Why is he special? Right? So if you say 4 kings plus 13 clubs out of 52, you're wrong, right? How is it different from this? Well, how many cards are king and jack?
8. Oh.
How many cards are, you have 1 card in your hand. How many cards you could say it's a king and a jack?
None.
None. If you have one of those, I'm not playing you any games. Oh yeah, 4 kings, no screw you. I'm not playing with you. You guys kind of with me? So how do I change this to make it right? How many cards did I count twice? 1 card I counted twice. You with me? There's all this math behind what we're doing right now. I just want you to see why it makes sense. And then we're going to eventually get to the formulas themselves. But the concepts make pretty good sense. I can't say 17. There aren't 17. Once I count all 4 kings, I've only got 12 clubs I haven't counted yet, right? I already counted the king of clubs. So it's got to be 4 plus 13 minus 1. 16 out of 52. Which reduces to 4 out of 13. Okay, cool. How we doing so far, you guys? Cool. So, or it seems increases the chances, but you have to be careful sometimes. Right? You might have to adjust it a little bit. And that's really what this is. And is a weird English word that gets lost sometimes, and math needs it. So this card has to be king and a heart. That's what king of hearts means. How you guys doing? Cool. So what if I said was probably? Oh, I just took away our. Oh, guess what? Was probably it's club or spade. Yeah, exactly. That would be half the deck, right? That's all the black cards.
Oh.
So that would be 13 clubs, 13 spades, half the deck. But if I say probability of a club and spade,
0.
yeah, it's 0. There are no cards that match both of these. So in math, the word and agrees with English sometimes. Sometimes and in English means it's this and that. To apply for the job, you have to have 4 years experience and a master's degree and must have decent clothes and whatever, right? So and it always restricts. But in English, I could say you and you, and that's why sometimes our brain thinks it's adding things together. No, that's another English interpretation of and. The math interpretation and is you have to do both of these things. And nothing does both of these. Cool. Okay, good. Okay. So let me take it back to some definitions here. So really, outcome should be first. Outcome is a single occurrence, something that can happen. An event is a collection of outcomes. So this is a single occurrence. How do I say this? Like a certain, you got a king of hearts, you got a ace of spades. You got this is single. That's an outcome. An event is a collection of outcomes. So collection of outcomes would be clubs, because that's 13 cards, right? So that's a collection of outcomes. Sample space is if I collect all of the possible outcomes and put them all down. So let's do an example with kids. Let's say I'm going to have 3 kids. What could the kids be? What flavor? What could they be? What gender? Boy or girl. Cool. And we're going to assume it's 50-50. And really, it's not quite, but it's close enough. What the hell? So we could get boy or girl. So one thing that happened, for example, would be boy, girl, boy, right? Now, how many of those could I write up there, do you think? How many do you think? How many choices are there for the first spot? 2. For the second spot? 2. Third spot? 2. So for every 2 of these, there's 2 of those. For every 2 of these, there's 2 of those. So there's a total of 2 times 2 times 2, 8. And so if you build a tree, we're not going to work with trees too much. Make a little tree. Boy, girl. So this is your first kid. So this is what happens. It could be a boy or a girl. It's just kind of like your path your life takes, right? Kind of with me? So it could go this way, it could go that way. It's like some weird sliding doors thing, if you've ever seen them. Then if after this kid, what could happen next? Boy or girl. So the second kid, and a third kid. So after this kid, I could have a boy or girl. And after these kids, I could have boy or girl, boy or girl, boy or girl, boy or girl. Thank God I didn't say 8 kids. So you can imagine, I mean, making these trees can get a little bit like, oh, please, stop. If it's a lot of things happening, or there's a lot of options in each thing. So I'm not going to do that to you. So what are the options here? There could be boy, boy, boy. Boy, boy, girl. Boy, girl, boy. Boy, girl, girl. And then sort of the same thing here. There. Okay. Let you guys think about it for a second. Any of you guys ever done logic tables? Anybody ever heard of that? Some of you guys, P's and Q's, true and false, exact same thing, right? The rest of you guys, forget that. Sure. One way to do this is the first guy could be boy or girl, and then you go boy, boy, girl, girl, and then you go boy, girl, boy, girl. So you can kind of make this list pretty quickly. If you're just trying to do it boy, girl, boy, girl, you're probably going to miss somebody, right? Now, are any of these events, and these are each events, right? Because they're each a collection of outcomes. That's the event of a boy first, a girl second, and a boy third. You with me? So each of these, are any of these more likely to happen? No, because there's an equal chance of boy and girl. We kind of at the outset agreed that it's a 50-50 chance of a boy or a girl. You kind of with me? So none of these are more likely. They're all then equally likely. How many of them are there? 8. So what's the probability that I would get a boy and then a girl and then a boy? Yeah, 1 chance of that happening out of 8. Now, more than likely, I don't know, maybe. If people would be worried about the girl being the middle child. But this couple, maybe they want 1 girl and 2 boys. So what's the probability of getting at exactly 1 girl? Yeah, there's 3, isn't there? There's 2 in the boy first. There's 1, 2, and then 3. Get a girl first, right? So there's 3 out of 8. And of course, if you think about it, exactly 1 girl, either that girl could be first, second, or third. So there's 3 chances to get 1 girl. You with me? What if I want at least 1 girl? Yeah, well, think about it. Think about it. What's an easier way to answer that question? What's the opposite of at least 1 girl? All boys. Yeah, so if there's 8 total, how many chances do I have to get all boys?
1.
So the rest of it must be at least 1 girl. You with me? So the probability of at least 1 girl is 1 minus the probability of all boys. It's 1 minus the opposite. And we know this already. The probability that that hurricane coming up Baja is going to hit us, say it's 1%. Right? It's not going to be a hurricane. It's not going to hit us. Whatever. I always root for that because I'm like, rain, please. So it's 1% chance. What's probably it's not going to hit us? 99%. You already do it automatically. You don't even realize what you're doing. But any opposite probability is 1 or 100%. 1 is the decimal version, right? Or 100% minus the other dude. That's how to get an opposite probability. We already do it automatically. Cool. So this would be 1 minus 1/8. So that would be 7/8. Or just count all the ones with a girl in and 7 of them. Cool, how are we doing so far? That problem was really easy because every outcome was equally likely. You with me? Since every outcome was equally likely, it was a very easy problem. So what we're going to be working towards is this kind of thing. Here's your classic probability problem. I have 4 red, 6 blue, and 8 green poker chips. Put them in a bag, right? It's your classic probability problem. Give me number 6, Jeff. 4 red, 6 blue, and 8 green. They want to do what I said. So, if I ask you a simple question, if I pick 1 chip, what's probably I get a red chip?
14.
Yeah, because there's 18 total. So 4 out of 18. Make that into a percentage for me. I don't know if you guys know this. Real quick, a little aside. 1/9 is what's 1/3 in decimal?
32.
Yeah, 0.3333. Isn't 1/3 3/9? So what's 1/3 of that? Would it be 1/9? 11111. So 2/9 would be 0.222. So it's 22.2%. All right, because that would be 2/9. You with me? All right. Or just do your calculator. Your brain. That to me is kind of neat. Most of us know 0.333.
Yeah.
Well, that's 3/9. So just cut it in thirds and you get 0.1. That's what 1/9 is. And now anything over 9 you could do. 7/9 is 0.7777. Right? Amaze your friends. I doubt that would go over that big. All right. So what if I said what's probably I get a green or a blue? I get a gorb.
14.
Yeah, green or blue would be 14 out of 18. Show off to me. Show off.
7.
Yes, cool. So 77.7 repeating percent. Kick ass. I like it. Okay, now, the thing we cannot currently do is we just don't know the math yet. It's much harder than that problem ever could hope to be. Is, what if I pick 2 chips? And let me say, with replacement. Now, all the probabilities of this problem are based out of what? They're all out of 18 to begin with, right? So if I take a chip out and I feed it to my little brother or something, now all the probabilities of anything else is going to be out of 17. So if I say with replacement, that means I don't feed it to him. He's going to be all right for a while. And I put it back in the bag. You with me? So you notice if I say with replacement or without replacement, it changes what I'm going to do, which is the basic heart of statistics. You got to know when you got to change your approach a little bit. So if I pick 2 chips, you could tell me what would be the least likely outcome. You can. What do you think the least likely outcome would be? 2 reds, because there's the fewest number of reds. But you cannot currently, unless you've taken this class before, you cannot currently tell me what the probability 2 reds would be. You can't just say, what would the sample space for this look like? What are all the possibilities for 2 chips? Red, red.
Red, blue.
Red, blue.
Red, green.
Red, green. Green, red. Green, blue. Green, green.
Blue, red.
Blue, red.
Blue, blue.
Blue, blue.
Blue, green.
Blue, green. Right, so there's 9 total things, right? 9 total possibilities. Why can't I use that the same way I use that? The kids.
Because they don't all have the same exact chance.
Exactly. Don't have the same probability. So I couldn't say red, red is 1 out of 9 because these aren't all equally likely. You guys kind of with me? That's why I love the question about what's the probability it's going to snow tomorrow? And somebody says, well, it could snow or not, so 50%. And that's my little brother. I don't know if I told him I'm a little brother. He says, Jeff, you teach statistics and probability. Why do you do that? Everything's going to happen or not. And that's when I say, I'm glad you didn't become a doctor, James. Right? What's my chances, Doc? 50-50. Right? You're like, wait. So probability obviously has a place in the world. People kind of tend to write it off because it can't tell you exactly what's going to happen. If you use probability to play poker, you must do it very often to actually have outcomes come out. You have to be very patient with it. People want some scheme that's going to get them to win the one time they play the damn thing. That ain't going to happen. That's called being super ass lucky. Right? You can't apply something and do it. So this is impossible for us currently. All right, so we're going to learn that pretty soon. But let me go back and focus on one thing real quick here. Something that seems very simple, but I want to make sure you guys really, really understand the idea behind it. If I flip a fair coin, so it's not weighted. So you didn't weight it to always come up heads or something. And it's got a head and a tail, right? Always check the coin. If somebody's going to flip their own coin, check that damn thing. Don't accept any wooden nickels. So if I flip a flare coin, what's probably going to head? One half. Now, what the hell does that mean? Because a really good point would be, if you flip a coin once, that does not mean a damn thing. You get half a head. What the hell does that mean? So probability, here's one reason why our brains can't quite get with probabilities. They don't make any sense unless you do it a lot. So this is an average over a long amount of time. So if I flip a coin 1,000 times, I should get close to 500 heads. If I get 900 heads, that's damn good evidence that the coin is weighted. You with me? So that kind of ties back to what we were saying earlier with chapter 1, statistical significance. Oh, God. Right? Okay. So this only makes sense in the long run. And this is called the law of large numbers. By the way, that is not my name for it. That is the name for it. It's called the law of large numbers. What this says is, if you do something enough, the probabilities will eventually equal to what you predicted. So if I took a coin and I flipped it long enough, I should start approaching 50% heads, 50% tails. Does everybody understand? Yeah. So if you flip a coin, does anybody have a coin? All right, cool. Maybe a few of you guys take it out. Let's see what happens. No, don't throw it at me. That'd be awesome. Normally, I'm okay with money being flung at me, but don't do that. It's not Friday night.
This is the same as law of averages, right?
What's that?
Isn't this the same as law of averages?
Yeah, law of averages is something we live by that says if I hit a bunch of red lights, I should hit a green light pretty soon. Yeah. So that's the idea of things averaging out for us, which actually is kind of like this. It says you could certainly hit 3 red lights in a row, but it's very unlikely that you'll hit every light would be red unless you got some major thing you should be there for, right? This is human perception. It's not really true. We just focus on the situations when that happened and we blow them up. And we think that always happens when, no, it doesn't. You guys kind of with me? So that's human perception versus statistics, and human perception will always win out in that case. So do me a favor. Whoever's got the coins, flip the coin once. Flip it. Whoever's playing. Okay. All right, cool. Now keep track of what you got. Now flip it again. Keep track of what you got. All right, you flipped it twice now, right, everybody? Now, how many of you guys got the exact same thing the second time? You did? Anybody else got the same thing? That is neat. All right, whoever got it again the second time, flip it again. I'm trusting you a lot here, by the way. I'm trusting more than I thought. All right. Same thing again? How about you? Dude, all right, 3 in a row. Do it again.
You didn't check their coin.
I know. I said I'm going off of trust.
I got different.
Different? You're the same?
Yeah.
Do it one more time. We got it.
Just fine.
Where'd you get that coin from?
Same thing.
Do it again. Do it again. Touch. All right. That's pretty good. That's 5 in a row. So, I mean, that was a little bit weird, right? I wouldn't expect to get 5 of the same thing. That's not quite like insanely weird. Like we wouldn't go running to somebody and say, I wish I would have taped that. It was amazing. But it is kind of like on the edge of, I wouldn't really expect that. And that's why people go wrong. If I ask each of you to write what you think is a random, like don't flip anything, just create a random list of outcomes, people would not have enough repeats. So if you made up one, you'd say head, tail, head. You might go 2 in a row, but you would try to kind of vary it up a lot. Whereas true randomness would say head, 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 tail, 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 head, head, tail, tail, tail. There's a lot more repeats than we would expect there to be, because every time I do it, everything's got an equal chance. So with statistics, it says sometimes it's going to happen. That goes back to that normal accident theory I was talking about earlier. When several things have to happen in a row, statistics says, oh yeah, that could happen. You better watch out. A lot more than you might think. Okay, that was neat. I like that. Yes?
I don't know. Would it be the same probability if you flip like 3 coins? Like you flip one, and right after you flip a different coin, you flip.
Oh, I got you. No, it's the same exact idea. Because a coin has no memory, but our brain thinks it does. Sort of like a slot machine. Has no memory. People go, man, this one hasn't given out any winners in a long time. I'm going to do it. It has no memory. It doesn't know if it's done it yet or not, right? Although the way they program those, it probably does. But a coin obviously has no memory. But if you flip a coin 5 times, where's my dude? 5, dude. If you flip it 5 times and it comes up tail, what did it come up each time? Out of curiosity. Tails. So if it comes up tails each time, the 6th time, there's no universal guarantee it's going to come up heads. It's possible there's a coin that you flip it and it comes up tails for all of eternity, right? I can just see that. It's a tourist thing, and you pick it up and you flip it, it's tails, yeah, and then finally I come there and flip it, it's heads, like, you destroyed it. Jackass. Okay. All right, but what I really want you to get there is the idea that if you do it over the long run, it should come out close to theoretical predictions. So if I have a fair coin, if I flip it 20 times, I could certainly get 18 heads. And it would be a little bit weird. But if I flip it 1,000 times, I really should be close to 500. I should be close to half, or else it's evidence that something's wrong with that coin. Okay. Hula. Oh yeah, so on page 137 in the new book, in case you're curious, that's where they talk about the law of large numbers. Let's see. Oh, so there's 3 main types. Oh yes.
You erased it, but when we pick 2 chips with replacement, and we pick 2 R's, and
Yeah.
we went back over it.
Oh yeah, we're nowhere near doing that yet.
Oh,
We'll eventually get there, so you just have to sit on that one.
got it.
Yeah, so I might ask somebody to look back at their notes and bring that example back up, and we'll calculate it later.
Okay.
Right now, we don't know enough math for it. 3 main types of probability. There's empirical. I think the book doesn't call it empirical anymore. It calls it, the new book calls it relative frequency approach. Yeah, sure. This would be if I don't know what the probability of something happening is. I just watch it. Like, I don't know the probability of a snake catching a gopher. So I just watch snakes over a long period of time, and I see how often they catch gophers, and I can calculate it, right? So, or I don't know how often tails will come up on a coin. I think it's not fair. So I flip it 20 times, and I get 18 tails. So the empirical probability of getting tails on that coin would be 18 out of 20. And you guys remember relative frequency is actually a term we used for histograms. And that's just where we divided the number divided by the total, right? So if I see 18 tails out of 20 total times, I just create that frequency, relative frequency, that's a percentage. 18 out of 20 is 90%. Cool. Okay, so that would be possibly evidence. 20 might not be enough, but that is semi-freaky. Right? I wouldn't exactly expect that, but it's not impossible. That's empirical probability is based on actual observations. The probabilities I've been doing mostly today are theoretical, what the book calls classical. I'm still going to call it theoretical. So the classical approach would say, if I have 6 sides to a die, what's probably going to get the side that's got a 3 on it? Well, it'll be 1 has a 3 on it out of 6 total sides. So I didn't just roll a die. I just thought about it. It was a thought experiment. It was a theoretical approach. Theoretically, this should happen. So if I roll a die 6,000 times, how many 3s would I expect to show up? Exactly. If I roll a die 6,000 times, 1/6 of those times should be a 3. So I would expect about 1,000 to show up. If I only get 17, that's really damn good evidence that somebody somehow has that weighted so a 3 won't show up. I'm not sure what game that is. Doesn't help you out with craps or anything, I don't think. And then the third kind we're not going to talk too much about is called subjective. And this would be if I ask you, what's the probability that you'll be late to school tomorrow because of a accident on the road? What do you think? What's your probability for that? Who drives to school? If you don't drive to school or take a bike or something, yes. So what would you say the probability is that you'll be stuck in traffic due to a car crash or something tomorrow morning? There's almost no wrong answer here. It's just based on your own experience, right? So if it's happened to you a lot recently, you'll go, oh, dude, it's like 50-50 at this point. Whereas if you haven't really had it happen to you and you've not been late, it's just been really slow traveling, and you're like, this barely ever happens, maybe 2%, right? That's subjective probability. It's based on your own experience. It's not even based on you observing and then calculating. That's empirical. You're not even doing this. You're saying, it's like 2%. It's probably not going to happen, but who knows? Where'd the 2% come from?
Your observation.
Out of the air. Out of your head. Right? Okay. So we're not going to talk about this one too much, which makes sense, because this is mostly a math class. We're going to talk about these two more often. Okay. So, a couple other definitions, then we'll get into the math behind the probabilities we were doing earlier. So the complement of an event. Very often we denote an event using capital A, capital B, capital C. So capital A could be rains tomorrow. So then the not rains tomorrow, I would capture that. Hopefully this book still does it the same way. Yay. No joke. So these are the symbols. So I have A is defined to be some kind of an event. The complement of that event is a complement, that bar over it. Sort of bad that they'd use the bar, because I'm used to the bar meaning an average, right? X bar. But in this case, it means complement. And why do you think they call it the complement? If you add up these two probabilities, what must it be? 100%. So this one complements that one. It kind of completes it, right? Aw. Cool. Okay.
So that's pretty much like saying like 1/10 or like, never mind.
Oh no, so this is like 100%.
Yeah.
So I'm going to put 1 because we're going to use decimals more often than percentages. Yeah.
Okay.
Cool. Oh, let's see. So this first section is section 4.2. It's pretty straightforward. They'll ask you in some places to create a sample space. So they're going to do the kids one again, the 3 children one. They like that problem. Even have one with 4 kids. I don't think I assigned that one. They're going to ask about complements. They're going to ask about converting something into a percentage. So if I said guessing an answer to a question, a multiple choice question has a chance of getting it right of 1 out of 5, what would that look like as a percent probability? 20%. Yeah, cool. So section 4.2, you've got to let that be simple. The new stuff really is sample space. You know how to create that, the sample space. So we did it a few times. We did it with red, 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 blue, right? We did it with boy, 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 girl. Okay. So before I want to get into a little bit more mathish stuff. So one of the main things we need to come out of this chapter with, understanding, is that OR is basically addition. Like we saw earlier, King or Jack was 8 out of 52. So I added those probabilities together. And we still got to learn what that is. So I keep teasing that, but that's the main one of the main things that come out of the section is what that means. And that's how we're going to learn what probability of red, red. Red and then another red. So I have to know what and does to things. We don't know yet. But OR is addition. So if I say what's probability of an event A or event B?
Both.
And let me give you a visual on this. I don't know if you guys have ever seen Venn diagrams. There's whole websites devoted to freaky Venn diagrams. A, B. So A could be men and B could be Republicans, for example, right? So if A was men and B was Republicans, who are these people? Male Republicans, right? And who are these people?
Non-male, non-Republican.
I like that non-male. That's how you identify yourself. Yes, I'm a single non-male person. So that would be female Democrats. I like it. Those would be male Democrats because they're not Republican, because not, and so forth. Right? So that's how you can read a Venn diagram, just in case you haven't seen these things too often. Hopefully you guys have seen Venn diagrams somewhere before. So if I want A or B, I want anything in A or anything in B. I'm going to take all of those. And in our English brain keeps saying that's an and, that's and. No, it's not. I don't want the people and would be, I would only take the male Republicans. And would say, you got to be man and Republican. Or says, you can be a man, take all them, or you could be a Republican. And then you can come on in the party. Right? You guys kind of with me?
Yeah.
I don't know what's going on there. I don't condone that necessarily, but so definitely I'm going to take all the men. I'm going to take all the Republicans. But if I do that, what have I kind of done? Which is really weird. Yeah, this middle part, which really that middle part we said was everything that was, minus all the people I've counted twice, which are the people that were A, men, and B, Republican. So that's exactly what we did earlier when we had king or club. We had 4 kings, 13 clubs, but we had to subtract 1, and that 1 was the card that was both king and clubs. How you doing? All right, so or is basically add. The reason I say basically is because it has this little adjustment to it. When would I not have to do this? when there's nothing in there, right? When I still do it, it's minus 0 then, right? So if A and B are what's called mutually exclusive. So you know what exclusive means, right? To me, that normally means I probably can't go there. Mutually means they do this to each other. It's not just one place saying you can't go here, it's the other place saying you can't go here either. So mutually exclusive things means there's nothing that could be both. Like hearts, clubs. They are mutually exclusive. If I said what's probably get a heart or a club, you could just add 13 to 13. There's nobody that's both. Are you with me? In a normal deck of clubs. Don't bring in your magic deck of clubs and show me. Deck of cards. Right? So if A and B are mutually exclusive, that means that the probability of A and B is 0. So then this does just become the straight up addition. So probably an A or B would just be probably the A plus probably B. If they're mutually exclusive. Now, personally, I want to show you this. But it's still the same stupid formula. It's just that I got minus 0. So the formula doesn't really change. It's just that that's a 0. Okay. So there will be some problems in there that talk about, here's a situation, are these two things mutually exclusive? And people have trouble with this. But for example, if they ask me, blah, 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 blah. Okay, this is very strange. Oh, and before I get too far away, they don't call it mutually exclusive anymore. They call it disjoint.
Disjoint.
That's right. Not that joint, but disjoint. I had to get that out there. Some people were thinking that. And again, you got to excuse me because I keep forgetting about, the way I've been used to doing it forever, and then the little words have changed for some reason. But that's really the same thing. Mutually exclusive just makes more sense to me. You can't go where, you can't go where. Disjoint, okay, they're not connected maybe. Okay, but they mean the same thing. So if they say, are these two disjoint or not disjoint? Strange examples they have. Blah, blah, blah. They're really into drug screening. Randomly selecting a person and getting somebody who believes in UFOs. Randomly selecting a person and getting someone who believes in the devil. Are those disjoint or not? And what you think is, can you imagine a person who matches both of those descriptions? Of course you can. There are probably whole groups of people that think the devil is flying the UFOs around, right? I'm sure there are. I bet you. Anything you imagine probably exists somewhere. You with me? So I can certainly imagine somebody who believes in UFOs and believes in the devil, so that would not be disjoint. There's at least one person in there, and they're overlap. Are you with me? This is not empty. That's how you think about this kind of problems. Just think, can you imagine? So if I had, some of these are just really gimmies. Arriving late for your next stats class, arriving early for your next stats class. Can that happen at the same time?
No.
That would be really neat, right? I'm not sure what that means. You've had some horrible accident, right? So that would be disjoint. That would be mutually exclusive. That would be disjoint.
In spirit.
Huh? Yeah, your spirit gets there before you.
Yeah.
And then what are you all about? You come in with these white eyes or something? Have you seen my spirit? No. I don't want to think about that. That's freaky. All right, so you guys cool with that? If you want to use the words mutually exclusive, I don't blame you. It's a little bit easier to understand. But disjoint means the same thing. Okay. Really, the only time... Oh, let's do a problem like this, and then I think I'm going to let us out early. Yeah, I thought that might get some... That's when you're most into it. Okay, just to warn you, I love this kind of problem. We've seen this kind of problem before, the setup. And normally what I do is I take a lot of the data you've given me and I create something like this from the data you've given me. So let's say that I go around and I talk to men and women. And I ask them some question, yes, no, Maybe so. Okay, so ask them, do you think Obama should authorize these airstrikes? Do you think he should put combat troops on the ground? And so I'm going to ask men and women this question. Let's see what happens. Okay. So then I could ask you all these questions, but the first thing I would do, now obviously this did not just actually happen. But the data I give you, I always try to make it data that you've actually given me. It's real data. I'm going to ask you questions like, what's the probability if I pick one person? What's the probability that they're a male? What's the probability that they said maybe? Questions like that. And then I'll ask you something like, what's the probability that it's a woman or they said no? So what do you think is a really good first step before you start attacking any questions?
Find the sample or the space, something.
I don't really need a sample space because I've got everything counted for me already. I just need to finish the counting out. So I know exactly how many men said yes. How many men said yes? 7. I just don't currently know yet how many total men there are, and I can't answer the question, the probability of picking a man, until I know. I don't even know how many total people there are until I count them, right? So a really good first step is fill in those outer spots, right? So consider how many total men are there up here represented. Good. For some reason, I always have people going the wrong way. This is the man row here, right? Like a man cave. And how many total women are up there? 20. How many total people said no? 25 people said no, right? 25 people said no. Do you guys see that?
Yeah.
Okay, good. Because I always assume people can read this correctly, but then they're looking the wrong way. But once you see it, your brain should click into it. People said yes. 12. People said maybe so. 4. Now, the next place where people make mistakes is how many total people are there? 41, not 82. Where would somebody get 82 from? They added these people and these people, but then they added those people twice, right? So there's really just 41, and the way you check yourself is add this, and it better come out to be 41 also. And thankfully it does. Once you get those up, you can answer any damn question I ask you. So what is probably I pick a man if I pick somebody random?
21 out of 41.
21 out of 41, good. Please, dear God, if you say 21, I'm going to say greater than 1, what the hell? Right? The probability can't be greater than 1. Or 100% if you have them in percentages, right? So be really careful. If you end up getting 1.8, which is 180%, do not just leave that there. Try, if you can't figure out what I'm wrong, say, I'm not sure. I know it's wrong, but I'm not sure why. And I'll take off fewer points because I'll be less worried that you think that that's an okay answer. You guys with me? You can't get something greater than 1. I don't care if your coach said, well, I gave it 110%. My coach said so. That's psychological. It's math. Okay. Maybe? 4 out of 41. Probably I pick a woman or somebody who said no.
37.
So you can be really smart about it. You can say, how many women are there? 20. Now, how many people who said no have I not counted yet? Do you guys see that? So you can either say 20 plus 11 out of 41, which is 31 out of 41, or you could say 20 plus 25. Are you guys with me? 20 women, 25 people said no, but how many people did I count twice? 14. So you got to subtract 14 off. And of course you'll end up mathematically at the same numbers, right? 31 out of 41. Either way you want to do it. But you can be smart about it. Just don't count the freaking people twice in the first place. What I love is when people do this and then they subtract 14 off again. No, don't subtract if you didn't count them twice. Okay, how are we doing so far? So what about 2 other questions here, and then I'll let us out. One we've done, and a new one that leads us into the next stuff. What's probably I pick somebody who's a man who said maybe. So what word is hidden in that phrase? Because English doesn't like to show this word often. And. They got to be a man.
Maybe.
And they got to have said maybe. Right?
3.
Make that grammatically correct if you want. Yeah. So 3. Everybody see that? So, and very often in algebra is called an intersection. Uses that symbol. Have you ever seen that symbol? In the or, it's got the upside down when you do interval notation. And it's got this symbol. It's called an intersection. And it's what's really awesome about looking at it like that is man, maybe, intersects there. Right? So 3, and again, notice it's 3. Say 3 out of 41. Now here's what's going to lead us into the next kind of level. Let me see what you guys think about this. Every single problem here is over 41, unless I could reduce something, but they all start off over 41, because there's a total of 41 people that could be. The only way it could be less than 41 in this problem is if I told you more about the person. So if I said, what's the probability I picked somebody who said no, given it's a woman. So you're given that it's a woman. You know it's a woman. What's the probability they said no, given that it's a woman? So how many people could it be?
14 or 20.
20. Because what do I know about the person? I was given that the person is a woman. So who can I ignore? The men. So it can only be out of 20 people. So the only time the bottom is going to change is when I'm given more information. I can then eliminate some people. I got a smaller denominator then. Right? So out of those 20 women, how many said no? 14. Good. So if I say given women, that means your whole world is that. And then no would be, where'd it go? Yeah, 14 out of 20. Cool. That was too close. Coolness. And on a test, let me say this right now. Let me say it because I'm going to say this a few more times. On a test, I definitely need to see this. You can then reduce it. You can then make a percentage out of it. But don't just give me a percentage and not give me any of the ratio work you did to get there. Because if you get it wrong and you don't show me this, I got to take off the most points because I don't know what you did wrong. Show me the ratio, and then you can go from there to wherever the hell you want to go. Cool. All right. I'll let us out really early. Don't get overly used to it.
Thank you.
Let me know if you have any specific questions about your test.